Well, I think solving logarithmic equations is a lot easier than exponential equations because there's far less options on what our equation can look like. Just like with exponential equations, we want to try to apply the one-to-one property first. And our one-to-one property for log says that if log base b is equal to, log base b of x is equal to log base b of y, then x is equal to y. So basically, if you can rewrite it as one log equal to one log with the logs having the same base, then the arguments have to be the same. That's always our first option. Now, the nice thing about log equations is we can know immediately right away when looking at it if the one-to-one property is going to work. If every single term in the equation contains a log, then the one-to-one property is going to be applicable. It may not be ready to go, but we can manipulate it so that we can use the one-to-one property. So if every term contains a log, you want to combine multiple logs on each side so that you have one log equal to one log. And we'll be combining logs using those log properties number 5, 6, 7. Once you have it one log equal to one log, you can simply set the arguments equal to each other. Now, if every term does not contain a log, then that means that we're going to have to rewrite it in exponential form. But again, it may not be ready to go. Before we can rewrite it in exponential form, we have to rewrite our equation one log equal to a constant. So you may have to combine multiple logs using our properties of logs before it is one log equal to a constant. Once we get it that way, then we're going to rewrite it in exponential form and solve it from there. Now we've talked that the domain for logarithmic functions is only from 0 to infinity. We know that the argument of a log has to be a positive number. So when you solve logarithmic equations, you have to do a quick check with your answer. You have to take your solution, plug it into the original equation, and make sure that the arguments are positive. You don't have to do a full check, just a quick check. Make sure that you don't get anything, a negative or a 0 in the argument. All right, so let's see it in action. We want to solve natural log of 3x minus 10 equals natural log of x plus natural log of x minus 4. The first thing I'm looking for is to see if our one-to-one property is going to be applicable. If every single term in the equation has a log, then the one-to-one property is applicable. Well, here, every single term has a log, so we're going to be able to use the one-to-one property, but it's not ready to go yet because I need to have one log equal to one log, and right now we have one log equal to two logs. So we need to combine these two logs on the right. The operation between the two logs is addition, so what are we going to do with the arguments to combine them?
Multiply.
We're going to multiply them, so we end up with x times x minus 4. Now that we have one log equal to one log, our one-to-one property allows us to simply set the arguments equal to each other and solve that resulting equation. We'll distribute on the right. We see that we have a quadratic equation. So to solve this quadratic equation, we're going to set it equal to 0, and I'm going to try to factor it, and if factoring doesn't work, then I'll have to use quadratic formula. I'm going to move everything to the right so my leading coefficient stays positive. We'll get 0 equals x squared minus 7x plus 10. This one will factor nicely into x minus 5 times x minus 2. Applying zero product property, we get x minus 5 equals 0 and x minus 2 equals 0. We get solutions of x equals 5 and x equals 2. Questions on the solving process? All right, well, now we got to quick check the solutions. We're simply going to take each solution individually and plug it into each of the original arguments. Make sure that you're plugging it in the very original, not what you've combined. So if I plug 5 in, do I get a positive number in each one of those arguments? I get 5, 5, and 1. So that one works. Now I'll do the same thing with 2. I'll take 2 and plug it into each one of my arguments. When we do that, do we get a positive for each one? No, actually I get a negative for 2 of them. The first one and the third one, I end up getting a negative. So I need to throw this solution out. We end up with one solution, x equals 5. Questions, anybody? All right, let's solve another. Here we have log base 4 of 5x minus 13 equals 1 plus log base 4 of x minus 2. Are we going to be able to use the one-to-one property on this one?
No, because there's a separate one.
That's right, because we have a term right here that doesn't contain a log that rules out our ability to use the one-to-one property. So that means we're going to have to rewrite it in exponential form. But before we can do that, we have to have a single log equal to a constant. So we want to get all the log terms on one side, and then we'll combine them. So let's subtract over. Our log base 4 of x minus 2. Now, a big mistake that I'll see with these types of problems is that people just don't use the properties to properly combine the logs, and they'll just like subtract the arguments or something like that. We can't do that. We need to subtract over the entire log, and then we're using our log property number 6 to combine. Since we are subtracting these two logs, what are we going to do with the argument when we combine them?
Divide.
We're going to divide them. We've rewritten our equation, a single log equal to a constant. Now we want to rewrite it in exponential form. Anybody want to give a shot what our exponential rewrite is?
Maybe 4 base 1.
Yeah, 4 is going to be our base.
Yeah. Over 1 equal x 5x minus 13 over x minus 2.
You got it. And now we're left with a rational equation. So sometimes over here, you'll have your base raised to a different power other than 1. So you want to start by cleaning that up. Here we just get 4. And now we have a rational equation to solve. How should we solve this?
Be cross.
Yeah, we can just cross multiply. Throw that 4 over 1 to make myself a proportion. And then we're cross multiplying. 4 times x minus 2 equals 1 times 5x minus 13. So that's going to be 4x minus 8 equals 5x minus 13. And we have a little linear equation to solve. So variables on one side, constants on the other. Subtracting 4x from both sides, and then adding 13. We get x to be 5. But before we are pleased with ourselves, circle our answer and move on, we need to quick check it in the original. So if we take 5 and plug it into either of these two original arguments, do we get a positive number?
Yes.
We do. So 5 is a good answer. Questions at all? Okay, let's solve 2 log base 3 of x minus 1 plus 12 equals 5 log base 3 of x minus 1. Are we going to be able to use the one-to-one property?
No.
No, because again, we have a term that doesn't have a log. So that tells us we're going to have to rewrite it in exponential form, but we're not ready because we need to have one log equal to a constant. So just like in the previous example, we need to get the logs together. So I'm going to move this one over here. We're going to get 12 equals 5 log base 3 of x minus 1 minus 2 log base 3 of x minus 1. We want to combine the logs that are on the right side. What do you notice about those logs that's different from any logs we've ever tried to combine before?
I have to take back exponent for the practice.
Say that again, Leila.
He has like 5 and 2 is exponent for that practice. You have to take
That's
it back.
true. There are coefficients, but
Yeah.
in our previous sections, we've combined logs that have the same coefficient. This one here is different from even those. Look for a more obvious answer.
Mhm.
The 5 and the 2 out in front.
Right, that's what she was saying too. But let's look at the rest of the log. What do you notice here?
They're the same.
They're the same. Same base, same argument. We have like logs. See, if we were going to combine these how we've done previously, we would have to make the the coefficient, take it, turn it into an exponent, and then we would have to divide our arguments because we have subtraction. But because these are like logs, we can simply combine them like we would any other like term. So if I have 5 of these logs minus 2 of these logs, that's going to leave me with 3 of these logs. So we can just combine them just like regular like terms. We could do it the other way. It's just going to be way more work. Questions on anything I did there? All right, is our log all by itself? It is, but we're still not ready to
We still
rewrite it.
need to divide by 3.
Well, that's right. We still got to deal with that coefficient because even though we have one log equal to a constant, that one log's not all by itself and it needs to be. So we have two different options. We can either take this 3 and make it an exponent, but like Anthony suggested, a way easier route to eliminate that 3 is just to divide both sides by 3 because I don't really want to end up with some binomial cube that I have to multiply out and then possibly use like rational zero theorem to factor. This will give us 4 equals log base 3 of x minus 1. And then we can solve by rewriting it in exponential form since I have one log all by itself, no coefficient equal to a constant. What's our exponential rewrite?
3 to the 4th equals x minus 1.
Perfect. 3 to the 4th is 81. We got a nice little linear equation. We get x to be 82. Before we circle our answer and move on, we need to do a quick check and make sure that when I take 82 and plug it into my original arguments, that I don't get a negative or a 0, and I don't. So this is a good answer. Questions at all?
When you're plugging it back into the log, you don't have to worry about the coefficients of the log.
Nope, we're just doing a quick check, kind of like with rational equations. You just quick check your answer in the denominator to make sure it didn't give you a 0. We're doing that same kind of thing here. We're just quick checking and making sure that our argument isn't negative or 0.
Okay.
Anybody else? And that's kind of really all the types of logs equations that there are. You know, you might have like ones that you can combine. You might be able to use the one-to-one property. If you can't, then you combine logs so that you end up with one log equal to a constant. Now, I could ask a different question, though, especially on a cumulative final. It's very common that instructors do that, where I'm going to ask you to solve a log equation, but maybe in a slightly different context. So if I asked you to find the x-intercept of a logarithmic function, f of x equals 5 log base 4 of x plus 3 minus 20, well, how do we find any x-intercept ever in our life? We let y be equal to 0 and solve for x. I know that I'm solving a logarithmic equation because my variable's inside the argument of the log. So I think I'm gonna let you guys solve this one. I'll put you guys together quick.
Just in case, teacher. Hello?
And everybody seemed pretty good on their answer. Everybody getting 253,0. Be sure that you're writing your x-intercept as an ordered pair. Questions at all? Oh, we jumped ahead. Okay, I'm like, what is this? How do we already do stuff? Okay, so we already did one exponential growth and decay problem. Remember, these are very similar to our variation problems where we're going to start with a generic formula, but here we don't have to come up with it. It's always going to be a equals a sub 0 times e to the kt power. We're going to plug information that we're given in for a sub 0, and t, solve for k. That'll give us a specific equation, and then we're going to use that specific equation to answer a question. So, you know, population growth is a very common application of exponential growth and decay, but now we're going to talk about a very common decaying application, which is half-life. This is something that we discuss a lot in chemistry. The isotope plutonium-238 is used to make thermoelectric power sources for a spacecraft. A spacecraft was launched with 2 kilograms of plutonium-238. If the half-life of plutonium-238 is 87.7 years, we want to write a function to model the quantity of plutonium left after t years. We'll round our k value to 5 decimal places, and then we'll use that formula that we come up with to answer the question in part B. Now, you may not have any experience with chemistry, and that's okay. I'm here to help you out through all that. An isotope is simply kind of like an offshoot of an element on the periodic table of elements. This number right here
With a different number of neutrons, I believe.
No, well, thank you. You know more about chemistry than me then. It's been like 20 years. So the 238 doesn't really, that's not a number that's going to matter for us mathematically. It's just part of the name. It's plutonium-238, so don't get caught up in that. what a half-life is how long does it take for half of a substance to disappear, to dissipate, to be absorbed, to evaporate, whatever, for it to go away. So how long it takes for half of it to go away. So we're looking to write a function to model the quantity after t years. We are always starting with the formula A equals A sub 0 times e to the kt power. We need to figure out our initial amount, A sub 0, the amount we're left with after so many years, and then t is however many years we're talking about. All right, so we're launching a spacecraft with 2 kilograms. So this right here is our initial amount. They go on to tell us that the half-life is 87.7 years. So that 87.7 is our t, because that's the amount of time. But you'll notice that they did not give us an A. That's not uncommon when we're dealing with half-life problems. If they gave us the original amount, and they tell us that the half-life is 87.7, that means that half of our original amount disappears in this amount of time, and A represents the amount we have after that much time. The A is always just 1/2 times A sub 0. So our A in this example is going to be just 1. But that's always the case with half-life. You have your original amount, and then A is going to be half of that original amount. All right, we have everything we need. Let's plug it in, solve for K, and then we will have our equation. So plugging in here, we're going to have 1 equals 2 times e to the k times 87.7 power. I'm going to do 2 things in this next step. I'm going to divide both sides by 2 because I'm trying to isolate the exponential, but then I'm also going to rewrite that exponent to say 87.7k. So 1/2 equals e to the 87.7k power. One-to-one property is not going to apply since our exponential base is e, so we're going to have to rewrite it in logarithmic form. Our logarithmic rewrite, since this is exponential base e, we're going to be using log base e, so that's natural log of 1/2 is going to be equal to 87.7k. And then we just divide to find our k value. Your k value is going to be a really small number, just like it was with our population growth. And this time, because our amount is decreasing, we anticipate a negative k value. So if we pop this in our calculator, we should get k to be negative 0.00790. So our generic equation then, they gave us our original amount, so we're going to call that 2. So A equals 2 times e to the negative 0.00790 t power. There's our equation. Questions at all on getting that equation? All right, let's use it to answer part B. If 1.6 kilograms of plutonium-238 is needed to power the spacecraft's data transmitter, for how long after launch would scientists be able to receive data? So they're giving us an A value here. So we're just plugging A into the formula we came up with and solve for T. 1.6 equals 2 times e to the negative 0.00790 t power. We're solving an exponential equation since the variable we're solving for is in the exponent. We know that's the technique to take. We'll start by isolating our exponential, dividing both sides by 2. Now that our exponential portion is isolated, we're ready to rewrite it in logarithmic notation. This is the natural log of 0.8 equals negative 0.00790t. And lastly, we'll divide. We get t to be equal to, and it says round to the nearest tenth of a year, so 28.2 years. This problem is different than this population growth here at Africa, where we talked about how we always round up because they were asking for like a calendar year. That's not happening in this example. They just want to know how many years go by until that happens. They're not giving us a year to start with. They're not asking for a calendar year. So there's no rounding up here. We're just rounding to the nearest tenth like the directions asked us to. Questions, anybody? All right, let's try another one. Another half-life problem. The half-life of thorium-229 is 7,340 years. How long will it take a sample of this substance to decay to 20% of its original amount? We'll round our K value to 6 decimal places and then round our final answer to the nearest tenth of a year. Well,
Okay, so real quick, for the previous problem, it was 28.2 years.
yep. So this problem is different than the last one. We know this 229 doesn't do anything mathematically for us. They say that the half-life is 7,340 years. So we know that's our T. But we also need an A and an A sub 0. In the previous example, they gave us an A sub 0, and then we got A by just cutting it in half. Do they give us an A sub 0 in this example?
No.
They don't. So what we do is we're literally just going to pick something. And this is only for these half-life problems, but when A sub 0 is not given, just pick something. And I'll show you that it really won't matter what we pick. I don't like to overcomplicate math, so I'm not picking 1,742, right? Like just pick a nice normal number for A sub 0. What sounds good to you?
0.
Okay, that's not a good number. Okay, sorry, any number but 0, right? Because I can't start with nothing, right? This has to be my original amount that I'm starting with. So pick anything, any positive number.
Well, glad I mentioned it then.
Yeah, right? So it's our original amount, so we need something that's positive. So just pick some nice positive number. What sounds good?
4.
4.
Okay.
Great. Well, before, up here in the previous example, they gave us A sub 0 but not A, but we were able to find A because since it's a half-life problem, A is just half of the original amount. So if we're choosing A sub 0 to be 4, that means that A is going to be half of that. A is going to be 2. And we've already established that T is 7,340. Now we have all the information that we need, and we can plug it into our equation. A equals a sub 0 times e to the kt power. So 4 equals 2 times e to the k times 7,340 power. And now they're kind of just all the same, right? We got to isolate the exponential portion. So we're going to divide by 2. See, I put my numbers backwards. Sorry. All right, so I'm going to divide by 4. Oh, that's going to give us 1/2 time. Sorry. 1/2 equals e to the 7,340k power. And then in order to solve this, we'll have to rewrite it in logarithmic form. But before I do that, I just want to, prove to you, because it seems crazy. I can just pick whatever I want for a sub 0, whatever. Let me show you why that always works out. So I'm just going to pick something else, a different number. I usually pick 1, but it doesn't matter. We can pick any number we want. Hell, I could pick 432 if I wanted to. I'd pick 1 though. A then is going to be half of that. And then we plug it into our equation. Well, the first thing we do is isolate the exponential by dividing by our coefficient. And notice that we get a half again. 1/2 equals e to the 7,340k power. So because a and a sub 0, one's half of the other, once you isolate the exponential, you're always going to get a half over there on the other side. So it absolutely does not matter what you choose for a sub 0. Just make sure that your a is half of that and you don't make some silly arithmetic mistake. That's why I typically like to choose 1, because I'm less likely to mess up if it's just like 1. But actually divide it in half. Jeez, man. See how nice that is? Basically, it just the 1 disappears and I don't have to deal with it. And we still get a half. So pick anything you like for a sub 0. Just make sure your a is half of that. You'll get the same answer every time. All right, let's get back to solving this. Rewriting it in logarithmic form, we're going to have the natural log of a half equal to 7,340k. And then we'll divide to solve for k. Again, we should get a negative k value because we are decaying, getting smaller. K is negative 0.00094, giving us the equation a equals. Now, they did not give us an original amount, so I can't just automatically put a number in for a sub 0 like I did in the previous example when they said, hey, we're starting with 2, and that's what we're going to use for the whole story. So a equals a sub 0 times e to the negative 0.000094 t power. Questions on obtaining this formula? Well, then let's use it to answer the question. The question is, how long is it going to take for a sample of this substance to decay to 20% of the original amount? We're going to have an a sub 0 and an a. And this time, since we're trying to figure out how long it takes to decay to 20% of the original amount, we're going to again choose any a sub 0 value we like, initial a, and then our a is going to be 20% times a sub 0, or 0.2 a sub 0.
20% is 1/5, so let's just choose 5.
Okay, that's fine. Again, I would choose 1. And Anthony, let me just show you why I would choose 1. Because, you're going to choose 5 and 1, and then when you divide, you're going to get the fraction 1/5. But if you always choose your a sub 0 to be 1, 20% of that is 0.2. And now when we plug it into our equation, we don't have that extra step of division because we have a 1 right next to the e.
Okay, I guess I was thinking 1/5.
Well, you're right. I
divided
mean,
by
that's what
20%.
0.2 is. If I divided both sides by 1, I mean, because if you put 1 over here and 5 over here, and then you divide both sides by 5, you're going to get 1/5. I'm just suggesting if we use a sub 0 equal to 1, we don't have that extra step of dividing. And if you can cut out a step, you can cut out the chance of making a mistake. Because that 1 kind of just absorbs into the exponential. Because we know 1 times anything is that other thing. You're not wrong at all. I just think this is, personally, I think this is a little bit easier. Our exponential is isolated. We're ready to rewrite it in logarithmic notation. Natural log of 2/10 equals negative 0.000094t. And then we divide.
Okay, I'm going to need to catch up.
No problem.
So natural. Okay.
So now we'll actually divide, and we get t to be equal to, and we're rounding to the nearest tenth, 17,121.7 years. I know this is a big number, but this number should make sense to us. So the way half-life works is it gives us a time period where half of the substance disappears. So in 7,340 years, half disappears. So that means we're at 50%. In another 7,340 years, half of that's going to disappear. So half of 50% gets us down to 25%. 20%, which is what we're decaying to, is less than 25%. So I anticipate a number that's more than double my half-life. Double my half-life would be 14,680. So I should end up with an answer that's more than that, and I do. So that can make me feel good about my answer. Questions at all? You will definitely see exponential growth and decay on the final exam. Absolutely. Many of you are taking this class as a prereq to get into chemistry class. So we are definitely going to be having this on the final exam. All right, Newton's law of cooling. This is the last problem I'm going to do in the whole course. I'm not going to do the last problem. This logistic growth model. This is it. Newton's law of cooling. Here we go. The temperature T of a heated object at time little t is given by the equation T equals C plus T sub 0 minus C times e to the k times little t power, where C is the constant temperature of the surrounding medium, T sub 0 is the initial temperature of the heated object, and K is the negative constant that's associated with the cooling object. So basically, what Newton's law of cooling talks about is if I take a hot cookie sheet out of the oven that was originally 350 degrees, so my cookie sheet's 350 degrees, I take it out of the oven, I put it on my counter, my house is 70 degrees. That's the C, that's the constant temperature of the surrounding medium. So my house is 70 degrees, and just how long does it take for the cookie sheet to cool off, cool enough so I can like pick it up. That's the kind of thing that's happening here. Okay, so an object is heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. We're going to start by using Newton's law of cooling to find a model for the temperature of the object T after T minutes. We'll round our K value to 5 decimal places. So this is very similar to the first step in the exponential growth and decay. We're going to plug numbers in for big T, C, T sub 0, and little t, and then we're going to solve for K. Then we will rewrite our equation plugging in our T sub 0, our C value, and the K that we found. See, the temperature of the surrounding medium stays constant, so that's not going to change, so that's why we can plug it into our formula. Also, the initial temperature is not changing, so we can plug that into our formula. So let's figure out what we were given. An object is heated to 100 degrees Celsius. What is that for us relative to our formula?
Is that T sub 0?
All right, that's our initial temperature. That's what we started heating it up to. It's left to cool in a room that has a 30-degree temperature. So what is that?
C.
C.
That's our
Yeah.
C value. And the reason that it says a constant temperature of a surrounding medium is because sometimes people cool stuff off in something other than their kitchen. You know, glass blowers take that molten lava and dip it into water, or sometimes things are put into sand to try to cool them down. So that's why they're generic and say a surrounding medium. All right, so after 5 minutes, so that tells us that's our time, little t, the temperature of the object has dropped down to 80 degrees. So that's our big T. That's our temperature after a certain amount of time has passed. We have all the information we need. Let's plug it into Newton's law of cooling and solve for K. 80 equals 30 plus 100 minus 30 times e to the k times 5 power. We know that we have to isolate the exponential portion of the equation to rewrite it in logarithmic form, but I'd do some cleanup first. You know, I'd subtract those numbers in the parentheses, fix my exponent. And now we want to isolate the exponential portion. So let's subtract 30, divide by 70. Now that our exponential is isolated, we're ready to rewrite it in logarithmic form. Natural log of 5/7 equals 5k. And then we're dividing by 5. We get our k value to be equal to negative 0.06729. Now we want to write the equation, and like I said, we're going to plug our t sub 0, our c, and our k value into the equation. It's going to be 30 plus 100 minus 30 times e to the negative 0.06729 t power. And I'd take a second and clean this up just so I had something easier to work with for our subsequent questions. So there's our part A. Questions at all?
So, do you still divide for this?
Well, but I'm not solving. Here I'm just writing the equation. Any other questions?
Okay, so how did you go from natural log to go to k equals you would have to divide?
Well, you mean
By
like from
5.
here to here?
Yeah.
Yeah, I divided both sides by 5. And I got my k value, and then I plugged it back into the generic formula along with c and t sub 0. We are going to use this formula that we just came up with to answer the questions in part B and part C. Part B says, what's the temperature of the object after 20 minutes? So how do we figure that out?
Plug 20 in for little t.
That's it. We're just plugging 20 in for our time, which is little t. We'll have t equals 30 plus 70 times e raised to the negative 0.06729 times 20 power. Do we have to solve an equation here? Like, are we going to have to rewrite it in logarithmic form and all that stuff here?
No,
Why not?
because everything's accounted for except for the t. We just have to plug it in.
That's right. See, the variable we're solving for is t. It's not located in the exponent. So this is not an exponential equation to solve. This is just something to shove in our calculator. Be sure that you put that product up in the exponent in parentheses when you put it in your calculator. And we're rounding to the nearest hundredth. Well, if it cooled down to 80 degrees in 5 minutes, after 20 minutes, I'm expecting it to be cooler than 80 degrees. And it does. It cools down to 48.22 degrees Celsius, which is still pretty hot.
T equals 48.22 degrees Celsius.
You got it. Questions, anybody? All right, part C, we want to know when will the temperature of the object be 35 degrees Celsius? What do we need to do to solve this part?
Plug 35 in for big T.
We're going to solve 35 in for big T and then solve for little t. So now that we're solving for little t, is this considered an exponential equation? Are we going to have to rewrite it in logarithmic form?
Yes.
Yes, because the variable we're solving for is located in the exponent. We need to start by isolating the exponential portion. So let's subtract 30. and then divide by 70. I think I'm going to simplify that just a little bit. That'll go down to 1/14. But we know we're going to plug it into our calculator, so if you don't feel like doing that, there's no reason you can't just leave it. Now we're ready to rewrite it in logarithmic form. Natural log of 1/14 equals negative 0.06729 t. And then the last thing we're doing is dividing. And we're rounding to the nearest hundredth. Now, if after 20 minutes, it only got down to 48 degrees, and now we're looking to be down to 35 degrees, I'm anticipating a number larger than 20, that it took more time. And we do. We get 39.22 minutes. Questions, anybody?
I didn't get the last part.
No, unshared too fast, huh? There you go. So that's the end of 103. Congratulations, you made it to the end.
Yay.
Yeah.
Okay, so on Wednesday, we're just asking questions and going over our work, right?
You got it. It's gonna be like an hour of office hours. I'm just gonna be here, and whatever questions you have, I'm gonna answer. I'm not coming prepared with anything. I never do. I already made you a final exam review packet with a fully worked out answer key, so I've already done all that for you. So I'm just gonna be here to field questions that anyone has. I would encourage you all to show up, because even if you don't know what to ask or feel like you have a question, somebody else might ask a question that's good for you, that will be helpful. I would definitely be taking like a serious amount of time. I don't know, the tests were so good, so I don't know if you guys prepared differently or if you just thought the material was easier, but I would definitely be spending a lot of time the next few days getting stuff organized, going through and indexing your book, writing out kind of review sheets, reference sheets for this exam, because you don't want to be thumbing through this whole book trying to find things. Yes, there's going to be one of every kind of equation. I haven't written the test yet, but yes, you're going to have to graph one of everything. I mean, that doesn't mean there's going to be 6 graph by transformation, but there's going to be graph by transformation. There's going to be graphing polynomials. There's going to be graphing rationals. There's going to be graphing exponentials and logs. There's going to be one where you have to rewrite as a product of linear factors or solve a high degree polynomial equation. You're going to have to solve exponential equations and logarithmic equations. I'm not going to pull a ton of stuff out of Unit 1 because most of that was review from the previous course, but definitely going to be circle stuff on there. You're going to have to complete the square to get it in standard form to be able to answer the circle questions. That's definitely going to be on there as well. Anybody, any questions for me? All right, well then have a wonderful day, and I will see you on Wednesday.
You do.